Let's talk about Stokes' theorem. So Stokes' theorem relates line integrals and surface integrals, and thematically it's very, very similar to what's going on in Green's theorem. It tells us that we can calculate a line integral around a closed curve by instead calculating a surface integral over what's inside that curve. And it tells us that the line integral is equal to the surface integral of the curl of that vector field. So the statement of Stokes' theorem is that suppose we have a curve that goes around the boundary of a two-dimensional surface, and we've got a vector field. Then integrating that vector field over the curve is the same as integrating the curl of that vector field over the surface. And here curl is curl in 3D. This is sometimes what we write as grad cross f, the thing that takes a three-dimensional vector field and produces another three-dimensional vector field. And we're going to have to make sure that orientations match up. We'll talk about what exactly I mean by that in the next lecture. Geometrically, what's going on is very, very similar to what happens with Green's theorem. Here we've got a curve which goes all the way around the outside boundary of this two-dimensional surface. And doing a line integral of our vector field adds up the total circulation, the total amount of push that the vector field gives to this track that goes around the outside boundary. And in some sense, it tells us if this curve is sitting inside a vector field, how much rotation, how much fluid rotation would be given to the stuff inside this curve. Whereas if we go over the surface, integrating curl over the surface tells us kind of how much spin is happening parallel to the surface. And by adding up those individual contributions, it tells us kind of the total amount of rotation. It's very, very similar. It's basically mathematically equivalent to Green's theorem once you write down the formulas, but it's thought of and played around with a little bit differently inside 3D.